Hello friends, today we are going to talk about stability of slopes. You have seen in recent times that the slopes, natural slopes, are becoming unstable, leading to landslides. And there has been in recent past huge loss of property and human life. Villages after villages have been washed away because of the landslides, because of the heavy downpour. So the stability of slopes are really very important. And in order to prevent this, what are the measures? So first, we will try to explain how you find out the stability of a slope. What are the different types of slopes? As you know, the slopes are going to be of two types. One is called infinite slope, and another we call it finite slope. As you know, the infinite slope is going to be of infinite extent, and here in infinite slope, we take the failure surface which is parallel to the outer surface, and therefore the gravitational force is acting in the downward direction, and the tangential force is acting in the uh, direction parallel to the failure surface. And there is the failure surface, and during the landslide, this chunk of mass is going to move in the downward direction. So the failure surface and this mass, if it is going to move in the downward direction, the gravity tries to pull it down, leading to landslides. This kind of failure, if the soil properties is going to be same at different depth, then this kind of failure, that is the failure surface being parallel to the outer surface of the slope, will occur. And in finite slope, which is of finite extent, as you see in different types of earthen dam or in highways, the slopes are going to be man-made and it is going to be of finite extent. Here the failure could be of the slope itself, and the failure pattern here is going to be an arc of a circle. So the failure pattern is going to be like this. This kind of failure is called slope failure. This is the failure surface, which in an arc of a circle. This failure can be also called a two failure. This is the two. If the failure surface is passing through the two, So it is called to failure. And this is the failure surface. And suppose the soil here below the two, that is in the base, is going to be quite soft or weak. The failure could be like this. This is called base failure. So this kind of failure is called base failure. So there could be in finite slope, there could be number one, slope failure. It could be two failure, or it could be number three, base failure. The failure plane could be different also, of different shapes. But normally it is going to be of this nature that we have discussed about over here. And we can analyze it. Let's say we are going to first talk about the infinite slope, how to check the stability. So this is important to check the stability of an infinite slope. Infinite slope is the one which is of infinite extent. Natural slopes. In India, in the Himalayan region, you have the infinite slope. And recently, in different parts of India, in the Himalayan region, you have seen in recent weeks, lot of landslides have occurred, leading to loss of life and property. Though that can be prevented, you can check the failure surface by reconnaissance survey or by aerial survey. You can find out, and you can take the remedial measures. So first, let us talk about the stability of an infinite slope. So we are going to discuss here the stability checks for an infinite slope. So friends, for an infinite slope, you will have to go for a stability check. How do you check it? The stability of an infinite slope. Let's say I take an infinite slope which looks like this. This is the infinite slope. This is the infinite slope. And the failure surface is parallel to the outer surface. So this is the failure plane or failure surface. And let's say the slope angle is beta. If you take a prism over here, let's say I take a prism. I may call this A, B, C, D. So ABCD is a prism. And let's say it is made of cohesionless material. So stability checks of an infinite slope which is made of cohesionless soil mass. So it's made of cohesionless soil mass. Let the soil property is known to you. Let the unit weight of the soil mass be gamma, and the width of this prism, this ABCD prism or soil element that you have taken, the width is B. So B is the width of the prism as shown in the figure. So AB equal to B. And let's say we take perpendicular to the board a unit distance, so unit length. Then what would be the this distance, horizontal distance? It will be B, because this angle is beta, it will be B cos beta. Therefore, the volume per unit length of the prism will be equal to this. This is going to be B cos beta, and let's say this is Z. The failure plane is situated at a depth Z. So it is going to be unit weight, that is gamma, multiplied by Z into B cos beta, multiplied by 1, perpendicular to the board. This becomes the weight. This becomes the volume. So this becomes the weight of the prism. Once you multiply it with gamma, the volume per unit length is Z into B cos beta, multiplied by gamma gives you the weight. So you can calculate the weight which will be acting at the CG. So you are able to calculate the weight of the prism. Therefore, the weight of the prism W, as shown in this diagram, is going to be gamma into B into Z cos beta. Therefore, you can calculate the vertical stresses which is acting over the failure plane. So what is the vertical stresses? Vertical stress will be weight of this prism W divided by the area. The area is going to be B into 1. And therefore, the vertical stresses, which is acting over the failure plane will be weight divided by area. So weight is already known to be gamma B Z cos beta, and the area is going to be DC equal to B multiplied by per unit length into B into 1. So BB gets cancelled. So it becomes gamma Z cos beta. Therefore, I can say that sigma V equal to gamma Z cos beta. So vertical stress is known to us. And because the slope angle is known to us, slope angle is beta. So if you want to find out the normal component here, normal to this plane, so it will be, this is the normal component, sigma n, this angle will be beta. Therefore, it is very simple now. The normal component sigma n, therefore, can be computed very easily. So let us write, therefore, normal stress to the failure plane, sigma n will be sigma v into cos beta. And sigma v, if you substitute gamma z cos beta, this becomes gamma z cos squared beta. So the normal component has been calculated. So this sigma v has got normal component. Also, perpendicular to the normal component, there will be tangential component. So the tangential component will be acting in the downward direction. It will be at right angle to this. And this becomes the tangential component, and this is called tau. This is the mobilized value, tau m, which is a function of the weight. So tau m can be calculated. So the mobilized shear due to the weight can be computed. So let's calculate it. Therefore, friends, we can calculate the tangential component, that is called the mobilized shear stress. So mobilized shear stress, tau m, it will be, because vertical component is known to you, it will be sigma v sine beta. So sigma n is going to be sigma v cos beta, and tau m, the mobilized shear, is going to be sigma v, and sigma v is already known to you, gamma z sine beta into cos beta. So this is the value of mobilized shear. This will try, this is tangential. And parallel to the failure plane, it will try to pull it down. It's acting in the downward direction, tau m. So this will try to pull it down. And therefore, the resisting shear, the ultimate shearing resistance, is the material properties, which depends upon the value of phi, because it is a cohesionless soil mass. So friends, we can very easily find out the resisting shearing stress, that is tau f, is given by Moore-Coulomb's theory, which is equal to C plus sigma n. C is 0 because it is a cohesionless soil mass, and therefore the cohesion will be 0. So this will be sigma n into tan phi tau f. Therefore, for stability checks, we need to find out the factor of safety. So factor of safety for an infinite slope made of cohesionless soil mass, the factor of safety F is given by maximum shearing resistance to mobilized shear stress. This is called factor of safety. So this is important. Tau f upon tau m. Now tau f is known to us, tau m is known to us. So equation 4 divided by 3, we can get the factor of safety easily. Therefore, the factor of safety F will be equal to sigma n, and sigma n is already gamma z cos square beta. So it will be gamma z cos square beta into tan phi upon tau m is gamma z sin beta cos beta. So gamma z sin beta cos beta. So friends, you can see that this gamma z is going to be cancelled out. So this goes out, and here cos beta and cos square beta. So it remains equal to factor of safety equal to tan phi upon sin beta divided by cos beta becomes tan beta. So factor of safety comes out to be tan phi upon tan beta, where phi is the angle of shearing resistance or angle of internal friction. So phi is angle of internal friction. Therefore, the factor of safety depends upon the value of phi and slope angle. So friends, for a stability checks, the factor of safety must be greater than 1, and therefore phi should be always greater than 1. So stability checks, very simple. We can say that for a stable slope, factor of safety must be greater than 1. should be more than 1.2. That is tan phi upon tan beta must be greater than 1, or angle of internal friction phi should be greater than the slope angle beta. So this is the important conclusion that you are going to get it. So always it doesn't depend upon any other fact. It depends only on phi and beta. Compare it. So if you plot here tau versus sigma n plot, C is 0. So friends, the tau versus sigma n for cohesionless soil mass will be given by tau f equal to tan phi into sigma n, or sigma n tan phi, where phi is this. So this is sigma n and this is tau. And if the slope angle, let's say this angle is beta, is less than phi, it will never meet the failure envelope, and therefore the slope will be stable. Slope stability is okay. So slope will be stable. The maximum value of beta could be phi, incipient condition. When beta equal to phi, the factor of safety becomes 1. When beta equal to phi, the factor of safety becomes 1, incipient condition. So beta must be less than phi, or phi should be greater than beta. This is a very important conclusion that we have been able to derive. And this is for cohesionless soil mass. The slope may be made of C phi soil. So if it is made of C phi soil, in the next video, I will let you know how to go for stability checks, how to find out the factor of safety if it is made of C phi soil. So infinite slope of C phi soil will be analyzed in the next video. So I only request you to see all the videos so that you are well acquainted with the stability of slopes. First, I will be dealing with the infinite slope. And what are the forces? One is the weight, as you have seen it. The weight is going to be a very important factor. If the weight is more, then you have got greater normal and tangential component. So one is the force of gravity, that is crucial for stability checks. Another is seepage. During rainy season, the water seeps into. So due to seepage, how it will affect the stability of the slopes, that also we will check it. So another force is your seepage. So all those forces we will see one by one. The drawdown, the slope is completely submerged and there is sudden drawdown, how the effective pressure is going to increase, how the weight is going to increase, everything we will see, and how it affects the stability of a slope. So in my next video, I will go for the stability check of C5 soil. So this was for phi soil. Cohesionless soil is also known as phi soil. So today we have done for stability checks for phi soils. So stability checks of infinite slope made of phi soils. In the next video, we will go for C5 soils. So friend, thank you very much.